All right, so we're going to start by looking at section 3.5, which is going to go over a lot of things we've already done before, finding roots. But this time, we might end up with square roots and have a negative under the root. So we're going to have to deal with imaginary or complex numbers. Okay, so just a reminder that when we've talked about roots, we've mentioned several different phrases. Okay, if a number is a root, it's also called a zero. It's also called an x-intercept. All those different phrases. When we start talking about roots that are imaginary, this one will not be true anymore. Okay? Because imaginary roots can only be found algebraically. You cannot graph on a calculator and find the imaginary roots. It's like if I graph a parabola like this and ask you where it crosses the x-axis, the answer is it never does. Well, it doesn't mean it doesn't have any answers. It just means it doesn't have any real answers. The two answers to a parabola like that would be imaginary. But if we are going to talk about real answers, and that'll still be part of what we do, then yes, the real answers are also going to be the x-intercepts. So if a polynomial does not cross the x-axis, there are no real zeros. What kind of exponent would a polynomial have to have in order for it to never cross the x-axis? Yeah?
Even.
Yeah, it would have to be even, because odd polynomials, the end behavior is up on one end, down on the other, and they're always connected. So an odd polynomial will always cross the x-axis, and even, not necessarily. So let's look at this equation. Y equals x squared plus 1. Just from the perspective of a transformation, we should already be able to tell there are no real solutions. It's a parabola shifted up 1, and it's opening up. So it's never going to cross the x-axis. So let's see what happens if we set that equal to 0 and try to solve it. So set it equal to 0. Bring the 1 to the other side. And how would we get rid of that exponent of 2?
Square root.
Right, we take the square root on both sides. So we get the square root of negative 1 equals x. And does anybody remember what that actually is? The square root of negative 1 is we have a symbol for it. Yeah? I. And I think we talked about that earlier on. So the square root of negative 1 is equal to I. So when you get an answer that has a square root of a negative, we generally wouldn't leave the answer like this. We would write this answer as I. So we have to talk about how do we simplify square roots of negatives. And that's a big part of it. Knowing the square root of negative 1 is I. So then what would I squared be? Yeah?
-1.
It would be negative 1. Because if you think of I is the square root of negative 1. And if you square I, the square and the square root cancel, and you get negative 1. So that's also another very important fact about I. If we are left with an I squared in an answer, we need to change it to a negative 1. So now, let's see what happens if we plug I in for x and then simplify. Let's fill it in. Okay, so I squared. What did we just say I squared is? Negative 1. And negative 1 plus 1 gives me 0. So what does that mean about I? In reference to that equation, x squared plus 1. That's,
Would it be like a root or solution?
yeah, it's a root. Right? We found a number that you can plug in, and when you plug it in, it comes out to 0, which means it's a root. A root or a 0. Is it an x-intercept? No, it's not an x-intercept. because it's imaginary. You can't see imaginary roots on a graph. All right, so what we're looking at in general are complex numbers. So we can write a complex number in what's called standard form. The standard form of a complex number is a plus bi, where a is the real part, b is the imaginary part. Now, some numbers don't have both parts. Okay? It is possible that you just have the number 4. Technically, 4 is a complex number. It's not an imaginary number, but it is complex. It has a real part of 4. It has an imaginary part of 0, I. Okay? So when you don't have an imaginary part, we just call that a real number, generally. And then these two are kind of the opposite. There's no real part. 3i minus 7i. Two separate. 3i and then minus 7i. Those are what we call pure imaginary numbers. Okay, they have no real part to them. If you want to think of the real part, it's 0 plus 3i. There's no real part. And then the last two examples have both a real and an imaginary part. That's probably the most common case when you're writing a complex number. Real and imaginary. So when I ask you for the real part of the number, that's, in that case, would be a 2. And when I ask you for the imaginary part, it's that right there, 3. Has an imaginary part of 3. So in order for two complex numbers to be equal to each other, it's a little different than just real numbers. Like if I said what real number is equal to 5, you would say, yeah? 5, yeah. There's only one thing you have to compare. One thing there, one thing there. When you want to know if complex numbers are equal, there are two things you have to compare. You'd have a real part, could be a plus or a minus, and then an imaginary part. And then you'd have another number over here, a real part, plus or minus, an imaginary part. You would have to make sure that those two things match, and you would have to make sure that those two things match. So the real part has to match the other real part, and the imaginary has to match the other imaginary. So it's not that complicated, but there are two things to check. If you had something like this, those are not equal. They're not equal. If you say, well, they're partially equal, well, the reals are equal, but the imaginaries are not. So they're totally separate numbers. All right, so a few rules when we do complex arithmetic. First thing to understand is that I, when we're using it with imaginary, that concept, I know in the English alphabet I is a letter, but we are treating I as a number. Just like in the Greek alphabet, in math. We never treat that as a variable. Never. Even though it is a letter, it's never treated as a variable in math. What is this always treated as? What does that represent? That's the name of it, and what does it represent?
A never-ending number.
Which is?
3.14.
Okay, so and it keeps going. So that's kind of the same concept with I. If you were doing a math like word problem and you had to pick a variable, you would never pick the Greek letter pi as a variable because it means 3.14 in math. Same thing with complex numbers. If you're doing a word problem and it's going to involve complex numbers, you would never pick I as a variable. Even though it is a letter in the English alphabet, it stands for a number that's written like that in math. Okay? But when you are combining like terms, the rules that you use with variables will work for these symbols. Like if you had 2x plus 3x, that is 5x. Right? And I'm using x as a variable in this case. Well, if you had 2 pi plus 3 pi, even though pi is not a variable, it's the number 3.14, when you combine like terms, you can write 5 pi. Even though pi is not a variable, it's a number. Same thing works with I. When you have 2i plus 3i, you're basically doing exactly what you did right there. 2 of a number plus 3 of a number is 5 of a number. In our case, that number is I. Okay, so that's how combining like terms works. When we multiply complex numbers, we are going to have to use the distributive property, double distributive, or FOIL. That's going to result in I squared coming up. We always want to change I squared to -1. So if you've left I squared in the final answer, you haven't simplified. When we divide complex numbers, we are not allowed to leave an I in the bottom. Just like we don't leave a square root in the bottom. The way we can get rid of an I in the bottom is to use a conjugate. If you don't remember what a conjugate is, I think we talked about it, but a conjugate is something like this. If you had a complex number 3 plus 2i, the conjugate is 3 minus 2i. The conjugate is when you change the sign of the imaginary part. If you started with 8 minus 7i, conjugate, 8 plus 7i. And the reason why we use the conjugate is because when you distribute, it causes some things to cancel out. And what we need to cancel out is the i's, and that's exactly what that does. It'll cancel out all the i's when you multiply them together. And then for square roots. So we do not want to leave an answer like that. You always want to simplify if there's a negative under the root. What number is really in front of x right now? Even though it's not written. Yeah.
-1.
Right, it's really like having a -1. When you have the square root of a product, you can take the square root of each factor separately. Okay? You can't do that with addition. Like if you have the square root of 2 plus 3, you can't say that that's the square root of 2 and then separately do the square root of 3 and add them together. That doesn't work. But with a product, it does. Like if I had to take the square root of 9 times 25, that will come out to 3 times 5. That you can do. So I'm going to break this up into 2 separate square roots. Square root of -1 times the square root of x. And what did we say earlier that the square root of -1 is? Yep, I. So when we write our answer, it's I square root of x. So the rule here is when you see a negative under a square root, the negative comes out as an I, because it's like taking the square root of -1. A couple different conventions when you write square roots that are imaginary. We're taking the square root of a negative to get an imaginary. If you have a square root left over, then you generally want to put the I in front. Something like that. We don't want to put the I at the end because it might look like the I is under the square root. This is confusing. I can't tell if the I is supposed to be under it or not under it. So anytime you're left with a square root, always put the I in the front. If the square root completely simplifies to a nice number, like let's say you have I square root of 9. Then you can put the I at the end. That's okay. Because in that case, the square root of 9 simplified to 3. There's no square root symbol left, so there's no confusion if the I is under a square root symbol, because there isn't one. Any question on those two notations? Okay. So let's try simplifying a few square roots. Let's start with square root of -4. JD, what's the square root of -4 going to come out to? Okay.
Plus or minus.
So there's no plus or minus symbol in front. If there was, then we'd have to take into account both. But right now, it's just the square root symbol, which means the positive one.
2i.
2i, yeah. Okay, so we get 2i. How about the square root of -7? What's that one going to be? Yep.
Would it be I root 7?
I root 7. Yep. So that's how you do that one. Okay. How about the square root of -9? Yep.
3i.
That would be 3i. And what about the square root of -20? Yeah.
2i root 5.
Perfect. 2i root 5. If you were doing just the square root of 20, it would be 2 root 5. When you simplify. But because we have the negative, that's going to come out as an I, and it should go right there. 2i root 5. Any questions on that? Okay. So now let's do an example of adding, subtracting, multiplying, dividing, and then we'll start actually doing the real part of the lesson, which is finding roots. Okay. When you add complex numbers, you combine like terms. You can combine real with real, and you can combine imaginary with imaginary when you're adding and subtracting. Don't try to do like 7 plus 2i and say that that's 9i. You can't add a 7 and a 2i. One's real, one's imaginary. They're not like, think of them as not like terms. Okay. So the operation they want us to do here is addition. What's going to be my real part of my final answer when I add these two together? Just the real part. Yeah? 11. So we get 11. And now what about the imaginary part? 2i. Yep. That's the final answer. There's nothing else you can do to simplify. Okay. Any questions on addition? Okay, subtraction, same idea, except think of this negative as being distributed. Okay, so that negative applies to both of the numbers inside the parentheses. 6 plus I. All right, so what are we going to get for, let's just do the real part, when you subtract those two complex numbers? Yep. Right, it's 4 minus 6. So that's -2. And what about the imaginary part? Yep. What is it? -3i. Yep. So -2i minus 1i is -3i. Okay. So for adding and subtracting, that's all you got to do. Okay. So next step, multiplying. Okay. When we're multiplying, that's a double distributive property, or FOIL. You're going to treat that just like you would do a problem like this. And I asked you to FOIL it. Okay, so let's distribute that out. 2 times 5 is going to give me 10. What's -2i plus 15i? Yep.
Would be
13i. And now the last part, first of all, it's a positive times a negative. Positive times negative gives me a negative. And what's 3i times negative I? Yeah?
Negative 3i squared.
Right, we got the negative 3i squared. Okay, so now we've got 10 plus 13i minus, what did we say earlier I squared is going to change into? Yep,
-1.
that's -1. So really, we're subtracting 3 times -1. We're subtracting -3, which is going to become +3. Just a coincidence, they both ended up as 13 in the real and imaginary. That doesn't always happen. Okay. Any question on multiply? Okay, again, it's not meant to be a full, like, blown lesson on complex arithmetic because it really is something you already did in algebra 2. Okay. And the last one is division. So in order to do division, we are not allowed to leave an I in the bottom of a fraction. Like that. Can't leave the I where it is. So we're going to use what's called a conjugate. So the conjugate of a complex number is when you change the sign or negate the imaginary part. You don't do anything to the real part. Keep that exactly the same. Conjugates is a trick that's going to come up a couple times. This is one time we use what's called a conjugate. We're also going to use it when we start talking about trig identities. So this will come back later on. All right. So let's say that we had the number 3 plus 2i. Anyone think they can tell me what the conjugate of 3 plus 2i would be? Yep.
3 minus 2.
Yep, 3 minus 2i. How about the conjugate of 4 minus 5i? Yep.
4 plus 5.
4 plus 5i. What about the conjugate of 3i? Yep.
Negative 3i.
Negative 3i. And what about the conjugate of 6? Yep.
6.
6 stays the same. Think of it as 6 plus 0i. The conjugate would be 6 minus 0i. Same thing. Okay, so now that we know how to find the conjugate, now we're going to use the conjugate to do division. So to divide two complex numbers like this, we don't actually do division, we do multiplication. And we end up multiplying the top and the bottom by the conjugate of what's in the bottom. Okay, as long as you multiply top and bottom by the same thing, you're not changing the fraction. You're manipulating how it looks and you're simplifying it by multiplying by the conjugate. Okay. So what's the conjugate of the denominator in this case? Oh, great.
So 5 minus I.
So we want the conjugate of what?
The 2 plus 3i.
Yes, conjugate of the denominator. So the conjugate would be
2 plus 3i.
2 plus 3i. Yeah. Now, because you're multiplying conjugates in the bottom, eventually when you do enough of these, you start to notice a pattern. Okay, I already know what the bottom is going to come out to. The bottom is 13, okay, just by looking at it. Let's FOIL that out and then see, how did I know that the bottom is 13? Okay, so when we multiply it, 2 times 2 gives me 4. What happens when we do 2 times 3i and 2 times negative 3i? Yeah,
They cancel each other out.
they're going to cancel each other out. That's a 6i and a negative 6i. So I didn't even have to think about that part. And then this part, You don't have to simplify the I squared, but can anybody tell me what's negative 3I times positive 3I? And leave the I squared for now. Yep. Negative 9I squared. I squared is negative 1. So you're really going to be doing 4 minus negative 9. What's 4 minus negative 9? Oh, Travis? 13. Yeah. So the trick, when you are multiplying conjugates, all you really have to do is take the number right there, square it, take the number right there and square it, and then add them together. 4 plus 9. That's how I got 13. Because that's exactly what ends up happening. And if you say, well, should I square the negative 3 or square positive 3? It doesn't matter. Because the negative cancels out. Okay, so we know the bottom is 13. There is no shortcut for the top. The top are not conjugates. You just have to multiply it all out and see what you get. So we're going to get 10 plus 15i plus 2 more I. So that's 15 plus 2 gives us 17i. And then I times 3i. What's that going to give me completely simplified? I times 3i. Yep.
Negative 3.
Negative 3. Good. Okay, so we already did the bottom. We know that's 13. And then the top, we're going to get 7 plus 17i. Sorry. We always want to make sure we write our answer in standard form. That's not standard form. Standard form has a real part separate from the imaginary part. So it's 7/13 plus 17/13. That's how you want to write your final answer. Just put each part in the numerator over the denominator separately. Okay, so that's a quick review of complex numbers and some of the complex arithmetic that we're going to have to do when we do roots. All right, so any questions on that? All right, now let's find some roots. Okay, so find the roots of x squared plus x plus 1. That's not a bad equation to have to work with. What makes this equation not that bad compared to maybe, say, that one? X cubed minus 1 versus x squared plus x plus 1. That one's easier. Yep.
All the zeros have to be measured.
We don't know that right away, but I mean, just looking at the two equations, maybe they're real, maybe they're imaginary. We'll see. But why is this an easier equation to solve? Yep.
Maybe because it's a quadratic.
Because it's a quadratic, right? You don't have to do rational root theorem. You're not going to have to do any kind of synthetic division, long division. You don't have to do any of that. Right? We just have to solve it using quadratic formula. When we fill it in, what's A going to be? 1. Yep. And B? 1. And C? 1. So all ones. So we got negative B plus or minus the square root of B squared minus 4 times A times C, all divided by 2A. Okay. When I simplify my radicand, What do I get for a number? Yeah, I get -3 under that root. How would you write the square root of -3?
Just be I squared root of 3.
Yep, just be I square root of 3. And that's it, you're done. All right. So because it was already a quadratic, that eliminated a lot of work. Just make sure you don't leave the -3 under the square root. You got to take that negative out as an I. Okay. Any questions how I used quadratic formula to get that answer? Okay. So notice the two answers that we got. Like if I actually write these out in standard form, it's -1/2 plus root 3 over 2I. That's the first answer. And the second answer is -1/2 minus root 3 over 2I. Those are the two answers if you write them out in standard form. What's the relationship of these two numbers to each other? They are what? Yeah,
Conjugates.
they are conjugates. And in fact, that will always happen. Anytime that you are solving an equation and there's going to be an answer that is imaginary, its conjugate is also going to be the answer, always. So what that means is when you are solving for roots that are complex with imaginary, they always come in pairs. You could never have one complex or one imaginary root in a problem. You could have 2 or you could have 4, or you could have none. But they always come in pairs. So if you know that a plus bi is a root, then you can be guaranteed a minus bi is a root. 5 plus 2i is an answer, then you know 5 minus 2i is also an answer. And again, that's assuming that the imaginary part isn't 0. Right? Because if the imaginary part is 0, then that kind of goes out the window. Because if you knew 6 plus 0i is a root, then you know 6 minus 0i is a root. It's the same thing. So all the theorems that we learned last week, remainder theorem, factor theorem, well, we kind of just use remainder theorem, synthetic division, they all work with complex numbers. Sometimes it's a little more work to do out the division, but we can still do division with complex numbers, just like we did with real numbers. Okay, so let's look at this one. They want us to show that 1 minus 2i is a root. Now, one way to do it, if you want to show that a number is a root, that means you can plug it in for the letter. And what would happen when you plug it in for the letter? You get what? Yeah. You would get 0. Well, I don't know about you, but I don't want to raise 1 minus 2i to the 4th power. Because that means writing 1 minus 2i with 4 sets of parentheses, foiling all that out. And that's only the first term. Then you got more to do. Okay. So I don't want to plug that number in to prove it's a root. What's another way that we proved a number was a root? We didn't actually prove that a number was a root. We proved something different, which meant it was a root. What did we prove that was different? Yeah?
The remainder 0.
Right, we proved that something was a factor. If you can prove that x minus your root is a factor, that's the same thing as plugging it in and getting an answer of 0. Yeah.
Is that 17 from the x squared?
That's 17, yeah. Okay, so we're going to prove that 1 minus 2i is a root by showing that x minus this is a factor. So x minus, and now we're going to put the 1 minus 2i on the outside of synthetic division. And we're going to hope that we get a remainder of 0. That's the hope. Numbers on the inside, what would those be? Yeah?
14, not 14, 4, 17, no, sorry, 0.
0, can't forget that.
17, 14, 65.
And 65. So when we get to the end, I'm going to hope I get a minus 65 with a plus 65, and then I get a remainder of 0. That's what I hope happens. Okay, so let's bring down our first term, 4. We're going to have a lot of arithmetic we have to do off to the side because we're going to be doing complex number multiplication. So we're not going to have room to do that in line with the problem. We're going to have to do it off to the side. But the first one we can do. What's 1 minus 2i times 4? And remember, it's a distributive property. Oh, Marcella?
4 minus 8i.
Yep, 4 minus 8i. That's going to be the easiest distributive property we have in this problem because we only had a single term times 2 terms. Now they're all going to be 2 times 2 terms. So they're all going to be FOIL from here on. Add your column. Now we have to multiply 1 minus 2i times 4 minus 8i. So that's what we're going to do off to the side. Multiply that out. We're going to get 4 minus 8i minus another 8i. And then we're going to get negative 2i times negative 8i. That is 16i squared, which is negative 16. Okay. What does that simplify to? And that's what I'm going to put under 17. Yeah. Negative 12. So we got 4 minus 16. Yep, perfect. And negative 8 minus 8 is negative 16. Okay. And now add that column. Yeah, that's fine. Negative 12, I'm getting a little cramped for space there, but it's okay. Negative 12 minus 16i. Well, there's nothing to combine with the negative 16i. So I'll just bring that down. But 17 minus 12 is going to give me, yeah, 5. Okay. Now do it again. 1 minus 2i times 5 minus 16i. It's not hard, it just does take a little bit longer when we got to do these multiplications out. So we're going to get 5 minus 16i minus 10i. And then negative 2i times negative 16i, that's a 32i squared, which is minus 32. What do we get when we combine all of that together? Yep.
Negative 27 minus 26i.
Negative 27 minus 26i. And now this is where I hope I get that negative 65 to get a remainder of 0. So we have one more multiplication that's kind of annoying to do. So 1 minus 2i times negative 27 minus 26i. Okay, let's see what happens. So we get negative 27. We get minus 26i. And And then here, we would get a plus 54i. Okay, so we just realized that we forgot to add these two together, and that's what I should be multiplying by. So we have to make sure we add those up. Negative 13 minus 26i. So that will change it a little bit. So now we've got 1 minus 2i times negative 13 minus 26i. And looking at that quickly, I think that's going to look good. That's negative 13. Now we get negative 26i. Negative 2 times negative 13 is a positive 26i. Negative 2i times negative 26i, that's positive, what's 26 times 2? 52, but it's 52i squared, which means it's negative 52. Those cancel out. And what's negative 13 minus 52? How much, Lance?
Negative 65.
Negative 65. Yep. And now when we add that last column, we get a 0. So that's my remainder. And we just proved that x minus this is a factor, which means this is a root, or a 0. Okay. Sorry about that one mistake. We had done everything right, we didn't add. All right. So, any questions on that? And we probably wouldn't have one too much higher than that power, because having to do 3 distributive properties, I mean, that's quite a bit in one problem with complex numbers. So it would probably be a 4th power or even lower. If it was lower, you'd just have one less column afterward. Okay, I think I already mentioned that at the beginning of class, why odd degree polynomials have to cross the x-axis because of the end behavior. So when we do a problem that's a cubic, okay, we are looking for 3 answers. Okay, a couple different cases could happen. We could get all real solutions. That's possible. Okay, crosses the x-axis in 3 distinct locations. We could also get all real answers, but only have 2 distinct. We could have something like this. Either way, when you're graphing, we could tell both of these cases mean you have all real solutions. 3 distinct, only 2 distinct. 1 is a repeat, which is okay. The case that gets a little bit trickier is if it looks like this. Does that mean that it's a triple root? Like if I were to graph x plus 3 times x plus 3 times x plus 3. It's the same factor repeated 3 times. The only number that would make that 0 is negative 3, filled into each of the factors. So that could be this case. Or it could be the case where there is 1 real answer and the other 2 are imaginary. So that's the trickiest one to figure out. So let's type it in so we can take a look at it. Maybe have an idea of kind of what we're getting into. So it's x cubed minus 1. And I'm going to do zoom 6. Okay, that's the trickiest case. Because we don't know, is that a triple root? Like, did I just graph x minus 1 times x minus 1 times x minus 1 if you factored that? Or is it just a single real answer and the other 2 are imaginary? Okay. So the way that we have to work with it is we've got to take this cubic down to a quadratic by hopefully finding a rational root. If we can't find a rational root, and you can't factor that, then you're going to be stuck. Now, if you knew the formula to factor a difference of 2 cubes, you could still do this problem without rational root theorem. But I'm going to guess most people don't know that off the top of their head. Okay. So we'll do it with rational root theorem. Okay. What would be my values for p, the factors of the constant in this case? Yeah.
-1 and 1.
Just -1 and 1. How about the factors of q? Factors of the leading coefficient. Yeah.
Also -1 and 1.
Also -1 and 1. So if this graph is going to cross the x-axis, add a number that can be written as a fraction. What are my options? What are all the p's over all the q's? Yep.
-1 and 1.
Just -1 and 1. And when we graph it, we already have an idea that it looks like it's going to cross at 1. So I'm just going to trace to 1, and I can see that it is an answer. When x is 1, y is 0. And now, what am I going to do with that 1 to take this cubic down to a quadratic? Yeah.
Use synthetic division.
We're going to use synthetic division. We're basically going to factor out that root. We're going to factor out x minus 1. And we already know it's going to give us a remainder of 0. I'm not interested in the remainder. I'm interested in the quotient, because that's going to give me the other 2 answers to this cubic. Okay, let's put the 1 on the outside. It's going to be a very quick synthetic division because all the numbers on the inside are 1s and 0s. So I filled in 0 for the squared and the linear term. Bring down the 1. 1. Add those up. Multiply. Add those up. Multiply. And add those up. Okay. So I now know that 1 is definitely a root because I divided and got remainder 0. Now, there's 2 other answers I need to find. What is the quadratic that I need to set equal to 0 to get the other 2 roots? Because remember, I don't have a cubic anymore. I'm down to a quadratic now. Yep.
X squared plus x plus 1.
X squared plus x plus 1. We already solved that problem earlier. Remember, a was 1, b was 1, c was 1? So now, once you have that, you would do what we did in example 4. Solve it with the quadratic formula, and these are your other 2 answers. -1 plus or minus root 3 over 2i. Those are all the roots to this problem. So it was 1 real, 2 imaginary. Any questions on that? Yeah.
I know that for like the second root, you could also make it separately. Like for example, -1 plus a rad 3 over 2i and the other root separately.
Yeah.
Like, which one would you prefer in like a test?
This symbol, I don't know if that symbol will pop up. If it doesn't pop up in Edulastic or Pair Assessment to use, then you'd have to write them separate. If the symbol is there for you to use, then I'm fine with you using it. Yeah, so either way would be okay. If you see some directions that say, write each of your imaginary answers in a separate box, well then you know I'm looking for you to write each answer separately. But I would always clarify that. Any other questions on this one? So if we go back to example 6 for a second, we basically, we were solving that equation. 0 equals x cubed minus 1. And the approach that I had you take to get all the answers was to use the rational root theorem, then use synthetic division, and then use the quadratic formula to finish off that quadratic. But what you really were doing was this. If you add 1 to both sides, you get that equation. And then how would you get x by itself in that equation? Yeah?
Cube both sides. Or cube root both sides.
Cube root both sides. Cube root, cube root. So what you end up with is the cube root of 1 equals x. That's the problem you just solved. You just found all the cube roots of the number 1. And there are 3 of them. And that is the process to find them. Now, most people, I think, would figure out the first answer. What's the real answer? Well, the cube root of 1 is 1. But the problem is, if you solve it using this method, how do you get these other 2? Negative 1 plus or minus root 3 over 2i. That's why I did it the way I did it. So what we did in example 6 is we really found the cube roots of the number 1. You might, in our book, see the term unity. Unity, I don't know why, they use that for the number 1. So like if it ever said to find the cube roots of unity, just means find all the cube roots of 1, which means to set up an equation like this and solve it. Okay, so you might have to set up your own problem to solve, like this. Find the 4th roots of unity. So you're going to have to figure out how to set your equation up first. Then you can do all your P's and Q's or whatever method you need to use to solve it. But this is the general format if they give you a problem like that. If they say to find cube roots of unity, that's the equation you would set up. X cubed minus 1 equals 0. Just change that to whatever root they want you to do. And that's exactly the problem we just did. X cubed minus 1 equals 0. If they want you to do the 5th roots, you would set up the equation x to the 5th minus 1 equals 0. But you can't just say, oh, I'll just add 1 to both sides and then take the 5th root. Okay, well, they'll give you one answer. X, the 5th root of 1 is 1, because 1 times 1 times 1 times 1 times 1 is 1. But how are you going to get the other 4 answers? They're all going to be imaginary. That's where you've got to do the P's and the Q's and all that. Okay, so let's see if we can set up the equation for this one. Find the 4th roots of unity. What would be the equation that I would set up? Yeah?
X to the 4th minus 1 equals 0.
Equals 0. And if you're unsure of yourself, try to solve that with like just regular algebra steps. You'd get x to the 4th equals 1. And now you'd have to take the 4th root of both sides. So yeah, you're taking the 4th root of 1 to solve that equation. But we can't do it that way because we won't get all the answers. You could get 2 of them that way. What if you wanted to know the 4th root of 1, what's one answer? Times itself 4 times gives you 1. Yep?
1.
1. And there's another answer that's easy to get. Yep? Negative 1. Okay, so there's 2. So we got 2 real. The other 2 are imaginary. Okay. Now, we could do the P's and the Q's. P would be all the factors of 1. Q would be all the factors of 1 again. But this is factorable. If you can factor it down to a quadratic, you can avoid the P's and the Q's and the synthetic division. And that's always faster. So, anybody have an idea of how that would factor? Yep,
X squared plus 1 and x squared minus 1.
yep, x squared plus 1, x squared minus 1. Now, you can check it. That gives you x to the 4th minus x squared plus x squared minus 1. Now you have two quadratics. You've already gotten it down to a problem you can solve with quadratic formula. But these quadratics are simple enough, we don't even need quadratic formula. We can just set each factor equal to 0 and solve. Okay, let's do the one on the right. What would be my first step to solving the one on the right? Yep.
Adding 1 on both sides.
Adding 1 on both sides, and my last step. Yeah.
Square rooting both sides.
And when you take the square root, how many answers do you get?
You get two answers.
You get
plus
two
or minus.
answers. Yep. And we can simplify when we take the square root of 1, 1, and negative 1. Those are the two answers that we were able to get right away without even really doing factoring. Okay, let's do the same thing over here. X squared equals negative 1. Take the square root of negative 1 and you get yep,
Would it just be I?
I. So here, if you want to write all your answers out, the four answers are 1, negative 1, I, negative I. So you're always solving for as many answers as that highest exponent. Any question on that? Yeah.
Wouldn't there not be a square root on the I? Because you're just saying like the square root of the square root of negative 1.
Wouldn't there be what?
Like for the answer x equals.
Oh, yeah. I'm sorry, thank you. Yeah. I think I said I think I said the answers right. I wrote it wrong. So I, negative I, 1, negative 1. Yeah. Those are your four answers. Yes, thank you. All right, so notice that in the problems that we just did, example 7 was a fourth root, 4 answers. Example 6 was a cube, and we got 3 answers. Example 4 was an exponent of 2, and we got 2 answers. Those will always match. Okay. So, in fact, we're going to just write down this second one. That one's the one I want to focus on. So the total number of roots always will match the degree of the polynomial. And that's called the linear factorization theorem. So if you've got a problem that has a highest exponent of 3, then you're going to be able to get 3 answers out of it. Maybe they'll be real, maybe they'll be imaginary. Something with a degree of 4 would factor into 4 factors. So that last problem we did, that had 1, negative 1, I, and negative I, these would be your factors. That's the one for negative 1. That's the one for positive 1. That's the one for positive I. And that's the one for negative I. Those are the 4 factors. X minus every root that I got. And these are 1s. These are i's. Now, there's nothing saying that the factors have to be distinct. When you factor a 5th degree problem, this is a 5th degree polynomial if you multiplied it all out. Okay, we're not going, but if you did, it would be something with an x to the 5th. -1 and +2 are what we call repeated roots. And the way that we describe how it repeats is we call that multiplicity. So -1 has a multiplicity of 2. That means there's 2 factors you can plug it into that give you 0. +2 is a root because you can plug it in and get 0, and you can plug it into 3 different factors. That's called a multiplicity of 3. All right, so the last thing we're going to look at is this. Find a polynomial with roots of 3 plus 2i, and what else do you know has to be a root? Yeah?
3 minus 2i.
3 minus 2i. So remember, to do that, like if I said to find a polynomial with roots of 2 and 3, you would say x minus 2, x minus 3. It's always x minus your root. That's what the factor is. Do exactly the same thing with imaginaries. If 3 plus 2i is a root, then x minus that is a factor. And if 3 minus 2i is a root, x minus that is a factor. And now to figure out what the polynomial would be, I need to multiply those two together. What do you think the first thing I should do inside the brackets on each one of those is? Jackson, what do you think we should do?
So I was writing the notes to the left.
So we want to distribute those out. So what do you think we should do first to distribute those out?
Like multiply so x squared and then
Something I would do just in the brackets first. Yeah.
distribute the negative.
Distribute the negative, yeah. So then you're going to have x minus 3 minus 2i. And you're going to have x minus 3 plus 2i. Now, hint, when you are writing a polynomial, there should not be any i's left in your answer. So somehow all the i's need to cancel out here. Okay, let's see what happens. So we're going to get x squared minus 3x plus 2ix. So that's the first one. Then we're going to get minus 3x plus 9 minus 6i. So there's the second one. Now I need to do the third one. That's a minus 2ix. Negative 2i times negative 3i is plus 6i. And negative 2i times positive 2i, that is negative 4i squared, which is plus 4. Okay. And now, what's going to happen there? So we have a negative 6i and a positive 6i. Yep. Yep.
The ix's were canceled.
Yeah, ix's plus 2ix, negative 2ix. Whenever you're writing a polynomial, if that doesn't happen, then something you made a mistake. So all we're left with now is x squared minus 6x, and then 9 plus 4 is 13. There's a polynomial, that's a quadratic, and the two roots are 3 plus 2i and 3 minus 2i. So now if you use quadratic formula on that, those should be the two answers you get. All right. Any questions on that? Okay, so that is 3.5. Okay, so that's homework tonight on 3.5. We'll go over that tomorrow, and I think tomorrow we're going to be finishing up chapter 3. So we'll be done with that.